Last class we have discussed how to measure the cream percentage in textile fiber from the load elongation graph. So we shall continue in the topic. So next I shall discuss about experimental methods. There are three principles of testing tensile property of textile fiber. One is the constant rate of loading shown here in this graph. Another is constant rate of elongation, and third one is constant rate of traverse, that is not shown here. So constant rate of loading and constant rate of elongation, these two principles are widely used for measurement of tensile property of textile fiber. So constant rate of loading is a principle by which a constant amount of load is added to the specimen for the measurement of its strength. And in case of constant rate of elongation principle, the rate of extension is fixed. That means a fixed amount of extension is given to the specimen for the measurement of its tensile strength. So if you use constant rate of loading, that means a fixed amount of load has been applied, then the load elongation curve will be like this. And if you are going to measure the tensile strength of the specimen by using constant rate of elongation principle, then it is observed that after a certain amount of loading, the material tend to be relaxed or slackened. Okay, so this is the slackening of the specimen. That means the material is easily elongated without the application of any load. So as the rate of elongation is constant here, so without the application of the load, the material will try to elongate. So this is one of the demerits of the constant rate of elongation principle. So now in this figure we shall observe the specific stress versus extension characteristic of various types of textile fiber. So here you can see the nylon, polyester, steel, carbon, S-glass, aramid, high molecular weight polyethylene fiber. Okay, from this graph it can be seen that the nylon and polyester, which are having very poor specific stress or the strength, whereas the steel, carbon, S-glass, aramid, high molecular weight polyethylene, these are the high performance fibers showing the high strength. So polyester and nylon are actually textile grade polymer. Okay, they are used for the apparel application or garmenting purpose. That's why high mechanical strength is not required. But a sufficient extension is required for the textile grade fibers. So that's why the nylon and polyester fiber are showing more inclination towards the extension axis, whereas the high performance fiber, which are having high modulus and stiffness, they have their inclination towards the specific stress axis. Okay, this is another graph of specific stress versus strain accounting a more number of textile fiber. Here also you can see the bast fibers such as flax, remi, these fibers are having a inclination towards the specific stress. That means these fibers are having high modulus and stiffness as well as high strength, whereas the wool, acetate rayon, viscose rayon, these fibers are having high extensibility. Okay, because they have their inclination towards the strain axis. Okay, they have the poor strength than that of the bast fibers such as flax, rami, durafil, etc. And they have high extensibility in comparison to those flax, rami fibers. Now I shall discuss about the variability, specimen length and strength, the effect of specimen length on its strength. The variability effect has been discussed by weak link effect. So we have to understand this graph where the strength versus length of the specimen has been plotted. Okay, the strength of the specimen or fiber specimen is measured for each and every point along with the length of the fiber, and this kind of trace has been observed. This is the trace or the strength of the fiber along with the each and every point of the length of the fiber. So now if we take the average value of all the strength, then S naught is the average strength or mean strength of the fiber. So if you measure the strength of the specimen for full length L, then the strength of the fiber will be come out as mean strength of the fiber will be come out as S naught. Textile fibers are not uniform. Their composition and fineness vary both from one fiber to another in a sample along with the length of the each fiber. Consequently, their tensile properties are also variable. Suppose that we could determine the strength at every point along the length of the fiber, which I have mentioned just. It varied from point to point. So point to point measurement of the strength of the fiber has been taken. It is gradually increasing load. If a gradually increasing load is applied to this whole specimen, it will break at its weakest point, S1. S1 is the weakest point, S1, which is the downmost position in the strength axis. Okay, this is the weakest point. Okay, this is the strength of this fiber. If the specimen is tested in two half length, each will break at its own weakest place. For example, we have taken the half length from this point to this point and another half length from this point to this point. Then the first half length will break from the value S2 and the second half length will break showing the value S1. Okay, so the mean strength of the fiber will be half into S1 plus S2. So mean strength S half is the measure on half length is the mean of S1 and S2 and must therefore be greater than the strength measured on the whole length. Okay, the strength measured on the whole length is S1. Now if we divided the length in two parts and take the average of the mean strength, which will come out as S half. So always S half will be greater than the value of S1. So similarly, if we going to consider the quarter lengths, for example L by 4 lengths for 4 specimens, and each and every case will observe the strength of the specimen here for S2, here for S3, here for S1 and here for S4, and then the mean strength will be equal to S1 by 4, which will be the average of S1, S2, S3 and S4, and which will surely will be greater than that of the S half. Okay, so S for the value of S4 will be here, which will be greater than S half. So it is now evidence that if you are going for measuring the tensile strength of the fiber for a shorter length, you will always get a higher specimen strength.